Welcome back to our part 3 of the second assignment in SPSS, and this component will address Yankee's pages 58 through 61, where he discusses inferential statistics, which will form the basis for most of the rest of the work that we do in SPSS. So let's start by taking a look at the differences between descriptive and inferential statistics. And likely most of you are very familiar with descriptive statistics, and these are statistics or numbers that characterize a particular data set. You're familiar with several types of central tendency. I think we start teaching this to our elementary students. The difference between mean, median, and mode. Most commonly we use mean, but sometimes other ways to measure central tendency of a data set are expressed. Dispersion is how spread out the data are, and typically variance and standard deviation are two ways to express that. They're actually related to one another, that the square root of the variance is equal to the standard deviation. And then the shape of the frequency distribution, two ways that we describe that is the skewness, or if it's stretched out, or asymmetrical. And then kurtosis is how peaked or flattened out the frequency distribution of the data is. So looking at inferential statistics, which again, this is really where we're going to focus most of our attention for the rest of this course, these are used to make generalizations about populations based upon a sample. And as you know, when we do research, it's very uncustomary to have the entire population to analyze in order to take a look at some research questions that you might have. So rather than looking at the entire population, we'll take a sample, which makes our job a little bit easier. But since we're not looking at everyone who could possibly be in the population, we have to make some inferences about that. And so some of the ways we do that is through some of the inferential statistical tests that you see here, such as t-test, ANOVA, correlation, regression, and the chi-square test, which we're going to spend really the rest of the course talking about these big five, because it's likely that if you choose to do a quantitative analysis that you'll seek out one of these types of analyses in order to make some generalizations to your population from where your data came. So let's take a look at the difference between populations and samples. Recall that a population is really all the members in a group that meet a specification that the researcher sets forth. So the researcher has an opportunity to decide how to define that population. So it could be all of the fourth graders in the United States. It could be all the fourth graders in the state of Texas. It could be all the fourth graders in a particular school district, or it could be the fourth graders in a particular teacher's class. So part of your job to express sort of the limitations and the parameters of your study is by defining the population. And in fact, the term parameter are the sort of statistics that are used to describe the population. So in populations, we have parameters, whereas in samples, we have statistics. And whenever we express parameters of a population, we use Greek letters as abbreviations. So you'll see mu for the mean, and sigma, lowercase sigma, for standard deviation, or rho for R, or the Pearson R correlation in the entire district, or the entire population. So that's a little bit about the population. So since we very rarely actually do what's called a census study where we look at everyone in the population, instead we'll take a sample, and using some sort of sampling method, such as simple random sampling, which fairly rarely occurs in education, or something called cluster sampling, where we would take groups of individuals that are naturally occurring, such as students in a classroom or a school, or we could use a convenience sample, which we're collecting information on students because people have volunteered to participate in the study. So all of those sampling methods sort of determine what your sample is going to look like and how similar your sample is to the population. So that's one of the considerations in sort of analyzing the results of your study, is to say, well, how well does my sample represent the actual population? So what is the sample? The sample is a subset of the larger population. And if we're describing the numbers or the data that are in the sample, we would call those statistics. And here are some abbreviations. You'll notice they're Roman numerals or Roman letters, and they're also italicized when used in APA formatted documents. So M would stand for the mean, SD would stand for the standard deviation, R would stand for the Pearson correlation coefficient. So one of the outcomes of the study is then once you get results, you could perform some sort of inferential statistical analysis, and then you would use that information to sort of make generalizations about the population. So if you saw a difference in your sample between a treatment group and a group that was a business as usual sort of situation where we just used our standard procedures that were in place rather than some specialized intervention, then we might want to say, okay, well, since we saw differences in our sample, then we're going to generalize that to the larger population to say, hey, if we did the same thing in the larger population, we might see similar sorts of differences between the groups. So really at the basis of any kind of inferential statistical analysis is this idea of null hypothesis significance testing. And this has caused many undergraduate and graduate students a lot of pain and suffering trying to understand it, and quite frankly, it is kind of a backwards way to look at things, and most of the pundits and statistical fields and research fields feel that it's kind of an antiquated way of looking at things. But nonetheless, you're required to use null hypothesis significance testing in your treatise, so it's important that you understand how to do that. Now, Yaki does a really good job discussing exactly how to set up null hypotheses based upon a particular analysis that you have planned. So he uses this and is very straightforward and gives you examples, and as part of your assignments for this course around these methods, you'll be required to use the same sort of logic. So in null hypothesis significance testing, there's really two types of hypotheses that you set forth before you start. The first one is the null hypothesis, and as the picture shows here, this is really kind of a straw man. Fisher, back in the 1930s, when he came up with the idea of a null hypothesis, used the word null because he felt that this was a hypothesis that the researcher would like to nullify or make incorrect. And so it's kind of the straw man that you set up so that you can knock him down, so that you can adopt an alternative hypothesis. So usually when we write null hypotheses, it's going to be about a state where there's really no difference. So we want to write it in such a way so that there's, if for example, we're looking at the difference between means for two groups of students who were subjected to different sorts of treatments, we would want to say as a null that there was no difference between the groups in terms of their means. And so in the bottom bullet here, you can see how that's formally written out, so that the null hypothesis is written as H, capital H sub 0, and then this is a typical way that we might write this. So the mean for group 1 is equal to the mean for group 2. And again, I just want to reemphasize that the reason why we set this up is because in most cases, we want to knock down that hypothesis and look at our data and reach a point where we're sort of suspecting that this null hypothesis may not be correct, so that we can adopt an alternative hypothesis. So let's look at that alternative hypothesis. And so this is signified as H sub 1. And then this would indicate that, well, if you if you reject or fail to reject the null hypothesis, then you might want to adopt the alternative hypothesis. And so here you can see if you reject the null, the alternative hypothesis would be, well, we saw ample evidence that that treatment might produce an effect or a difference between the groups. And so here you can see how that would be written out in this particular case, that our our alternative hypothesis, H sub 1, is that the mean for group 1 is not equal to the mean for group 2 in this particular case. Now, if you have other hypotheses out there and different sorts of tests besides the t-test, then that would look a little bit different, but those are some of the details that Yaki will go into in our subsequent chapters. So part of your decision making as a researcher is to decide whether you want to test that null hypothesis or adopt the alternative hypothesis using a one-tailed or a two-tailed test. Now, the idea of tails comes from frequency distributions and sampling distributions, and as part of this, I'm not going to go into the details of that, but for right now, you should know that really this is about directionality of the alternative hypothesis. So in a two-tailed test, this basically is asking the question, is there an effect of a difference between groups either in one direction or the other? We don't really care whether one's greater than the other. We just want to see if there's a difference in means between the two groups that you've identified. So it really is multi-directional. And a big advantage of using a two-tailed test is that if you don't know going in whether your treatment's going to increase performance or decrease performance, it allows you to sort of test things out and just say, is there going to be a difference because of this treatment that I've provided for my participants in the study. A disadvantage of this is that it actually is not quite as powerful as a one-tailed test, so it's a little bit more difficult to determine whether a significant effect has been identified or not. So the other possibility obviously is the one-tailed test, and in a one-tailed test, up front you decide that there's some directionality. So your alternative hypothesis might state, as shown here, that the mean of group 1 is going to be greater than the mean of group 2. So if you had some sort of theoretical evidence or you had some sort of suspicion that the treatment that you provided to group 1 was going to cause their outcomes or their performance to be greater than that of group 2, whatever that might be, then you could put some directionality to it. Now, the good thing is, since you've decided up front that there is going to be some sort of directionality to the outcomes, you really have a greater chance of finding a significant effect because it increases the power of your statistical analysis. However, if for some reason group 1 happens to be significantly less than group 2 in terms of their performance, then you wouldn't be able to officially come out and say that because you had sort of set the directionality prior to actually performing the study. So part of your decision making before going into a study would be to decide if you're going to use a one-tailed or a two-tailed test. Now, by convention, Yaki is going to use the two-tailed test overall in all of the analyses, so that's sort of the default, so that might be the direction that you would want to go. However, there can be some specific cases where a one-tailed test might be a better choice for you to make. So where the idea of one-tailed and two-tailed tests come from is basically the ends of the normal distribution, and if you're looking at whether a certain result falls to the one extreme or the other, and you don't really care which end it falls in, that would be a two-tailed test because it would fall within two of the tails of the normal distribution. However, a one-tailed test is directional, and so you would only be looking at one of the tails of the normal distribution in order to kind of figure out whether there was a significant difference between your two groups in this particular example that we've been working with. So that's where the one-tailed versus two-tailed comes from.